Okay, everyone, let's take a look at polygons and some things that we can learn about polygons. First of all, what is a polygon? You can see I filled out some of these blanks just to save us a little time here. If you want to go ahead and pause the video and fill in the blanks and just listen to my explanation, you could do it that way, or you can fill in the blanks as we go. A polygon is a figure that's formed by three or more coplanar segments. So let's go ahead and let's start by drawing something that might match these definitions. Let's draw a polygon with four segments. It says three or more, so we'll go with four. First of all, we need to make sure each segment intersects exactly two other segments, one at each endpoint. So let's do 1, 2, 3, and 4. So let's make that last one actually intersect. Let's make it connect nicely. There we go. Okay, so let's take a look at this polygon right here. You can see it's got four segments, right? It's made up of just straight segments. Each one of these segments is intersecting two other segments at the endpoints only. So you can see we have this segment here. Let's throw some labels on here. We'll call that, oops, I need my drawing tool. We'll call this point A, point B, point C, and point D. So you can see segment AB is intersecting at one endpoint, it's intersecting segment BC, and at the other endpoint, it's intersecting segment AD. Segment AD is intersecting segment DC at one endpoint, and at the other endpoint, it's intersecting segment AB. And we can kind of go around this polygon and see that each one of these segments is intersecting two other segments, one at each endpoint. And also, it says no two segments with a common endpoint are collinear. In other words, we're not making, we're not just kind of lining up segments, if you will. So what does that mean would not qualify as polygons? Well, first of all, if we use something that's not a segment, if we use something, if we make something with maybe a curved side, so if we did like this, that would not be considered a polygon because of this curved side right there. Yes, it has two segments that are straight, or that I at least try to draw straight, but that curve right there means that that's not a polygon. Also, if I drew something that maybe, let's get my drawing tool out. Let's see if I did something like this. That would not be considered a segment. Let's see if you can figure out why. If I look at this segment right here, that's not a polygon because this segment is only intersecting one other segment right there. And the same thing with this segment. It's only intersecting one other segment right there. Another example of something that wouldn't kind of fit the bill as a polygon might be something like this. And the reason why that wouldn't work is because we can see that this segment right here is intersecting this other segment, but not at its endpoint. It's intersecting somewhere other than the endpoint of the segment. So none of those would be considered polygons. But as long as we're looking at three or more segments that intersect two other segments, one at each endpoint, we're looking at a polygon. Now, we can kind of break polygons into two groups, convex or concave. A convex polygon is something like what I drew up here, or if I want to draw another one, I'll draw one with 5 sides. It would look like maybe something like this. A convex polygon, if I made a convex polygon with 5 sides, maybe it would look something like this. 1, 2, 3, 4. I'm sorry, this is a concave polygon. I think I might have said convex a second ago. That's a concave polygon. So what makes this different than this? Well, one way I think about it is I think about the concave polygon as something that's kind of caved in, whereas the convex polygon maybe it hasn't caved in. It doesn't have like a corner that's kind of pointing towards the inside. By definition, what we're looking at is it's convex if we made each side of this polygon a line. So let's extend each side a little bit further into a line. So I'll extend that side in both directions. I'll extend this side in both directions. Come over here and do this side in both directions. Make this side go further in both directions, and finally make this bottom side go further in both directions. What you'll notice is none of those extended sides went into this space in here, which would be considered the interior of that polygon. All of those extended sides stayed on the exterior, the outside of the polygon. That means it fits the bill fits the description that I've got here, that I've got for you right here. None of the lines containing sides of the polygon also contain a point in the interior of the polygon. Now if we look over here at the concave polygon, we're okay if we extend this side. This side extended stays outside the polygon. This side extended also stays outside the polygon. This left side extended stays outside the polygon. But then as soon as we extend these two sides, you'll notice that what happens is, right in here, those extended sides go into the interior of that polygon. And so that makes it a concave polygon. So we know what a polygon is and what a polygon isn't. We can see how to divide them into convex versus concave. What about how we name polygons? Let's take a look at that next. We name polygons by listing vertices in consecutive order, and it's important here about this consecutive order. So if I wanted to draw a pentagon VIKNG below, let's see, we would make a pentagon has 5 sides. You probably already knew that. In a minute here we'll talk about names of polygons with other numbered sides. So we need 5 sides to our polygon. There we go. And so we have vertices here. Sorry, we have vertices here, 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 and here. And it says this is going to be pentagon VIKNG. So if I call this V, then vertex I either has to be this one or this one. I can go in clockwise order or counterclockwise order. Let's go counterclockwise. So that would be vertex I, and then that would make this here vertex K, this would be N, and this would be G. Now that's not the only name for this polygon. I could have also started here with N and called this polygon NKIVG. Or I could have started with N and went counterclockwise and gone NGVIK. Or perhaps I would have started with K and gone clockwise and be KIVGN. All of these, and there's obviously more, all of these would be okay names for this polygon. What I can't do is I can't maybe start at V and then just kind of skip over to N and then skip back to I and then go to K and then go to G. That doesn't work. All right, so let me cross that off because I didn't list the vertices in consecutive order. I kind of jumped all around across my polygon there. So a polygon with 3 sides, we probably already know that one, right? We've talked about that one before. That's called a triangle. If the polygon has 4 sides, some people would be tempted to maybe call it a square or a rectangle, but those names are special versions of 4-sided polygons. The general classification of 4-sided polygons we call quadrilaterals. Quadrilaterals. A 5-sided polygon, is a pentagon. We just drew one of those over there. A 6-sided polygon is a hexagon. I remember that one because it has X in it, just like the word 6 does. Hexagon. We'll skip 7. 7, if you wanted to know, you could call it either a septagon or a heptagon, but we don't use that very often. An 8-sided polygon, you probably are aware of. This is like a stop sign, right? It's an octagon, right? That prefix oct usually refers to the number 8. And we'll skip 9. 9 sometimes is called a nonagon. A 10-sided polygon is called a decagon. And if we get over 10, there are some other polygons with more than 10 sides that have specific names. But generally, once we get past 10, we just call it a n-gon, where n is the number of sides. So it might be an 11-gon or a 12-gon or a 13-gon. And you'll see some examples of that coming up in a minute. So that's the naming of polygons. Another term you need to know about polygons is what if you connected, let me grab a different color here. What if you connected 2 non-consecutive vertices? So if I connect vertex I to maybe vertex N right here, or if I connect vertex K to vertex G, those lines that I just drew there, they are called diagonals of the polygon. So if I wanted to draw all the diagonals of this pentagon, see, I already got 2 of them there. I need to connect G to I, and I need to connect V to N, and I need to connect K to V, and that should be all of them. Look, I made a nice little pretty star in there. But that would be all the diagonals, right? K is connected to the two non-consecutive vertices G and V, and so on and so forth as I go around that pentagon. So the diagonals of a polygon can kind of give us an interesting idea about how the sums of the measures of polygons, what they come out to be. If I add up all the angles of different sized polygons, different size in terms of number of sides that they have, what does that sum come out to be? In other words, if I have a four-sided polygon, what do all these angles add up to? And if I have a five-sided polygon, what do all these angles add up to? Will it be the same? Will it be different? Well, first of all, remember we know that in a triangle, which is a polygon, the angles in a triangle always add up to they always add up to 180. Now let's see, what if I take this four-sided polygon, what if I take this four-sided polygon and I draw in one diagonal? Boom, right there. I just broke that four-sided polygon, that quadrilateral, into two triangles. Now I know that if I add angles 1, 2, and 3 up, so if I say the measure of 1 plus the measure of 2, forgot the number 2, plus the measure of angle 2 plus the measure of angle 3, I'm going to get 180. And then if I number these 4, 5, and 6, and if I add the measure of 4 plus the measure of 5 plus the measure of 6, I'll get 180 there. And now if I add 1 plus 2 plus 5 plus 6 plus 4 plus 3, that would be all the angles inside my quadrilateral, right? So the measure of angle 1 plus the measure of angle 2 plus the measure of angle 5 plus the measure of angle 6 plus the measure of angle 4. I'm going to run out of room here. Let's come down here. Plus the measure of angle 4 plus the measure of angle 3. Well, that's going to be 180 for 1, 2, and 3, right? The 1, 2, and the 3 are going to give me 180. And then another 180 for the 5, 6, and the 4. So that's going to be 360 degrees, right? The two triangles together are each 180 degrees. So when I put them together, I'll get 360. What about if I have 5 sides? What if I draw all the diagonals from this vertex of my pentagon? Well, that would be those two diagonals. So with my 5-sided polygon, with my pentagon, I just made 3 triangles. Now what do you think I'm going to get if I add up these angles, 1, 2, 3, with these 3, 1, 2, 3, with these 3, 1, 2, 3. If I add all those up, I'm going to get 180 plus 180 plus 180, or in other words, I'll get 3 times 180, which is 540. Now if I add another side, what if I look at a hexagon with 6 sides? Well, if I draw all the diagonals from this vertex of my hexagon, I'd have 1, 2, 3 diagonals, and I'd make 1, 2, 3, 4 triangles, right? 1, 2, 3, 4 triangles. So if I added up all of those angles, it would be 4 times 180, which is 720, right? There's 4 triangles there, so that'd be 4 times 180 for 720 degrees for all of the angles inside my hexagon. And one last one, let's do a 1, 2, 3, 4, 5, 6, 7-sided, one of those either sevengons or heptagons or septagons, sometimes you'll see them called. Well, if I drew all those diagonals with my 7-sided polygon, I get 1, 2, 3, 4, 5 triangles. So that angle sum would be 5 times 180, which is 900 degrees. So a 7-sided gives me 900, 6-sided gives me 720, 5-sided 540, 4-sided 360, and of course we know a 3-sided polygon would be 180. So every time we add a side to our polygon, we're actually adding 180 degrees to the angle sum. Well, what if we have a 27-sided polygon? Do we just want to add a whole bunch of 180s? Well, no. Thankfully, we can have a little formula, right? If our convex polygon has n number of sides, where n could be anything more than 3, right? It could be 3 sides, it could be 23 sides. The sum will be n take away 2 times 180. See how that worked out in there? A four-sided polygon, 4 minus 2 is 2, and 2 times 180 gave us the 360. For our five-sided polygon, if we take away 3, if we take away 2, we get 3. 3 times 180 is 540. Our six-sided polygon had 4 triangles. 4 times 180 is 720, and so on and so forth, right? So number of sides minus 2 times 180, that's the sum of the measures of the interior angles. Now what about the exterior angles? What about the exterior angles of a polygon? Well, this one's a little bit easier. If I draw one exterior angle at each vertex of a polygon, doesn't matter what kind of polygon it is, whether it's a triangle or a quadrilateral or a pentagon, if I add all those exterior angles up, I will always get 360. So let me show you what I mean here. Let's go back to this pentagon VIKNG. If I make an exterior angle right here, if I make an exterior angle right here, call that angle 1, and I make an exterior angle right here, call that angle 2, make one right here, call that angle 3, make one right here, call that angle 4, I skipped 4 there for a second, and one right here and call it angle 5. If I add angle 1 plus angle 2 plus angle 3 plus angle 4 plus angle 5, I'll get 360. And if I did it down here with my hexagon, I'm not going to draw it out, but if I made one exterior angle at each vertex, those would also add up to 360. It doesn't matter how many sides I'm looking at, those exterior angles will always add up to 360. So in example 1, we have the measures of the interior angles and the sum of the measures of the exterior angles for a 7-sided polygon. We've actually already done this once, right? But just to kind of show you how the formula would work, we would take 7 minus 2 and multiply it times 180. So that would be 5 times 180, which is 900, right? So that's the interior angles. This is the interior angles, gives us 900. The sum of the exterior angles will always equal 360. So that one's easy. If I have a 17-gon, so a 17-sided polygon, I'm not going to draw this one out, that's for sure. If I want to do the interior angle sum, I would take 17 minus 2 and multiply it by 180. So that's going to be 15 times 180, which is going to give me, let's see, what's that going to be? 2,700 degrees. 2,700 degrees is what all those interior angles would add up to. The exterior angles, it's going to add up to 360. Because it doesn't matter how many sides there are, the exterior angles always add up to 360. Okay, one last thing. This video is getting a little long. I'm going to try and breeze through this pretty quick. One last thing about polygons. We can look at polygons and we can describe them either as equilateral, which means all the sides are the same length. Or we can maybe describe them as equiangular if all the angles are the same measure. Or if they are both equilateral and equiangular, we can call them regular. So this guy down here would be a regular pentagon. All his sides are the same length and all the angles are the same measure. So that's a regular pentagon. So I'm going to leave this last example here. I want you to try and figure this out. You have to find the measure of one interior angle and one exterior angle for each of the following regular polygons, right? A regular quadrilateral, remember that's 4 sides. Find one interior angle and one exterior angle, slightly different than what you did up here in example 1, right? Up here in example 1, we were doing the total, the sum. Now you're just looking at one interior and one exterior for a quadrilateral, an octagon, and a 20-gon. So I'll leave that up to you guys. See if you can try and do those, and I'll see you next time.